Hi, my name is Boris Shingarov. I work at LabWare. I make VMs, virtual machines. Now, to exclude any confusion, I'm talking about dynamic language VMs. For interpretive languages with JIT compilers, dynamic garbage collection, that kind of stuff. Today I'll talk about formal, specifically in the context of open source compiler toolchains for open source ISAs. Now, a couple of people over the past few days been asking, why this talk? Why concentrate on this? They were like, hey Boris, you're usually more associated with your being one of the originators of the Eclipse project. So they wanted me to talk about building open source software ecosystems. And here's the thing. Back in 2001, the important question was the top-of-the-art idea. Can open source have that kind of best programming environment? So today, if you ask me today what an equivalent driving issue is, well, as far as I'm concerned, we're talking about software tools here. Today, an equivalent issue would be rigorous engineering. So let's talk about the way programmers write software. We write code, we write tests. We run the test. If the test passes, we're happy. It appears to work. So, for example, imagine we are implementing addition. And we want to see whether 3 plus 4 indeed computes 7. We run it, and voila, indeed it does. We're laughing. Well, what about 10 plus 15? Does that work? I don't know, not from this test. What about corner cases? This doesn't tell me. So we have potential latent bugs. And these are exceptionally difficult, especially in something like an optimizing compiler. Now, it's not like I'm trying to diminish there's a whole exciting art of TDD, and that's not going anywhere, that's not disappearing, because ultimately the process of cognition is when you're watching the computer work through a concrete example, that's how you develop an intuition of what's going on. And yet at the same time, there is this altogether different way of thinking, going back to the ancient Greek geometers, which asks, can I prove that this is computing x plus y for all x and all y? And the second idea, due to Hilbert, is that proof is just another mathematical object. And in a computer, you can compute it just the same way as you do with ints, strings, lists, whatever. So programming becomes all about computing proofs. There are many factors why. You see, when I first encountered this 30 years ago at the Skobeltsyn Nuclear Physics Institute in Moscow, it was about things like nuclear safety. The project I was working on, we did instruments for cardiovascular surgery. You see, all stuff where human lives critically depend on. And back then, it was a very specialized niche. Today's growth happens in directions into fields that require this level of assurance. applications where if you tell them it appears to work, they'll simply not talk to you. This is one very general factor. Another is that it's becoming so difficult to track all the logic as to cross into impossible. And there are more non-trivial reasons than just complexity. Some are specifically caused by what the term computer architecture means today. See, when you write a compiler for something like the classical System 360 or x86, you test it on the chip you happen to have in your shop, and chances are it's going to work on your customer's chips of that ISA. With something like Power, you cannot do that because the standard only defines behavior up to subtle details about concurrency. This is called weak consistency. There's an envelope of allowable behaviors. You test your compiler on one processor and it works. Your customer in production has a processor with out of order that interacts slightly differently with the store buffer, and you get weird race condition bugs. Good luck debugging those. I mean, in theory, you could try to be careful and separate what you see the chip is doing from what the book actually promises, but good luck tracking all those details as a compiler writer human. The third factor is that when trying to bring up a new processor, the software tool chain is what anchors you down. You want to be flexible about what you can do in the processor. In reality, you change something and GCC breaks. And it takes a year to find that subtle cause. That's why all that auto-retargetable CGen and all that target agnostic stuff. So how do we begin to have something better? I'll go by examples. One general idea is to build an abstract CPU with two distinguishing characteristics. One, I want it to be symbolic. That means its state, the contents of its storage bases, is algebraic formula as opposed to concrete numbers. Two, I want to infer it from a machine-readable spec. Once I have this abstract CPU, I proceed with tests as if I were just programming normally. Remember 3 plus 4. But I give it x and y instead of 3 and 4 and watch what comes out. Now, let's formalize what I want. What I'm going to do is I'm going to ask a satisfiability solver to search for a case where the result is actually wrong. Well, that means output is not x plus y. And if it finds such a case, then, well, here is a bug, right? That's a ready bug report. And if it says unsatisfiable, that means that I have proven that all the cases are actually correct because, well, it exhausted all the combinatorial space of all the different combinations of possibilities. All right, very good. So we've gone from tests to model checks. Is there a problem here? Turns out, yes. And that problem is the unbounded case. You see, programs have loops, and as the result, when we try to decide whether behavior A is equivalent to behavior B, we bump into a fundamental problem called the halting theorem. And the root cause of that turns out to have actually nothing to do with programming or computers. It's a fundamental problem that has been disturbing the smartest mathematicians for at least 2,500 years, going back to Plato and to Pythagoras' school. The good news is that very recently, I'm talking just a few decades, we've seen some real progress. There are now things like intuitionistic type theory, and these are applied in practice to build systems like Kami and CompCert. The bad news is that today in 2020, this is still remaining very science intensive. It takes tremendous R&D investment to prove relatively modest software. And for cases like dynamic languages, we are still not there. There's a lot of very interesting research going on, people trying to prove JVMs and etc. I attempted to build an intuitionistic Smalltalk VM, but a final engineering science for this kind of thing doesn't appear within reach yet. Then what does appear within reach? So let me show you the system for toolchain synthesis we've got here at LabWare. It's all open source under MIT. This is all written in Smalltalk because Smalltalk still remains the best tool for conceptual exploration in the spirit of Alan Kay's Dynabook, where instead of drawing shadows on the wall and trying to back project things into your imagination, you can just directly experience them. Computational mathematics, some people call it. Before we dive in, I must explain something. This has been an evolving system that grew over several generations. So I personally find when I try to explain how it works, I find it unavoidable to touch upon some historical points, how I develop it over the years. When we first decided we wanted to synthesize the toolchain from a spec in a processor description language, for a number of years our PDL was ArchC. ArchC is a System C-ish TLM level modeling language. You describe structure, for example, what your registers are, like this here is from the model of 32-bit PowerPC. You describe in a very natural DSL your binary encoding. This is naturally split into, you've got instruction formats, and then you've got individual instructions. These are like so. Then you've got specification for the grammar of your assembly, like so. And obviously this is invertible in the sense that you can recover an actual working assembler and disassembler from this. So at the binutils level, this has served us very well. Obviously, ArchC has been around for a while. Many people have synthesized binutils from these specs, so there's nothing unusual about this. The approach itself is even more well understood. CGen
The Lisp system for doing this kind of things has been there for decades. Where things become difficult is semantics. At first, we were encouraged. Obviously, for the symbolic CPU, we need a special kind of bin utils that will propagate algebraic expressions down to what I call holes in instruction memory. You see, when I try to prove something about behavior, I don't have the code set in stone. In a JIT, it's all self-modifying code, which is okay. It just means the instructions the CPU is executing are themselves algebraic instructions. So here's Open Smalltalk JIT on PowerPC. This is not actual cog. This is our JIT. This assembler syntax here, the grammar for this gets automatically embedded into the compiler from processing the ISA spec. So this comes from here, and this other one is because of parsing this here. Okay. But what's much, much more non-trivial is that we have two levels of variableness. This emits the code to put a 32-bit immediate into a register. So the immediate is an argument to the JIT. That's the first level of variability. The JIT will know IMM when it's called to generate the code. But because we are trying to prove that this works for any IMM, we symbolically execute this with IMM equals X. Here's the bytecode that this source gets compiled to. This here is a bit vector AST in the Microsoft Z3 prover. So these are ready-made instruction encodings. At runtime, the JIT just spills them onto the instruction stream. Once again, how does this work? Here is an explanation of the same instructions in the context of OMR. That's the universal VM substrate underneath J9. This is from last year's Splash. So we're trying to put X, which is a bit vector length 32, into GPR3. This is PowerPC again. OMR is just a C++ program. So we execute this function symbolically. And as the output, this is what it puts into the code cache. This. Then we jump to this, and then we execute it. And then we look at what's in GPR3. It's going to be some bit vector 32 AST. We're trying to prove that the value of that AST equals X for all values of X. Well, that's easy. We just ask the SMT solver to find one that doesn't. The solver goes over all 4 billion values, because it's 32 bits, right? Comes back saying, I cannot find any. Voila, there is your proof. Goes over values conceptually. These days, solvers grew a lot smarter than to literally iterate over all combinatorial cases, which is why this kind of analysis is practical. Now, let's go back to this slide. What's the difficulty? The difficulty is semantics. How to recover from the PDL information about what to put into GPR3? This is where we got stuck regarding argc. in ArchC, how they synthesize simulators is they attach a fragment of C++ to each instruction. That's really not suitable for automated reasoning. However, what we had high hopes for was an ArchC extension called ACC-Gen. What it is kind of RTL for declarative instruction semantics. They have a super optimizer that transforms this RTL into an LLVM backend. I wrote my own ACC-Gen processor, which I call the Prolog Instruction Generator, or PIG, which is based on equational logic programming. It's the Van Emden equational conditional rewrite engine, and the rules are the RTLs. This does work as a proof of concept, but we found that to practical applicability, ACC-Gen is rather limiting. Therefore, there was the question, what else can we use for the semantics part? We investigated some other analysis systems. Alive is used by LLVM to prove correctness of optimizations. Anger is a binary analysis system which is used actually for many things, such as security vulnerability analysis. You throw a power or ARM or MIPS binary at it, and it automatically finds buffer overflow exploits. That's one thing you can use it for. We have used that to analyze behavior of dynamic compilers. That work is all open source, but there is a number of challenges that all bump against the same fundamental fact that for CPU binary code, this goes through this Valgrind lifter library, which, apart from being a monster lump of C++, is itself a non-symbolic beast, which on self-modifying code ends up not useful. Valgrind just plain doesn't know about certain things. We talked at the beginning of this lecture about race conditions due to weak consistency on power and on RISC-V. It's not gonna help you there. Well, RISC-V, it doesn't know about RISC-V, period. Which brings us to Sail. Sail is a language for rigorous specification of ISAs. It's designed to be accessible to engineers without a killing learning curve. It's real in the sense that those models are precise and complete. It's the language the RISC-V folks write the normative definition of their ISA in. Now, that being aside, the argument here is about availability of tools. So you want enough precision to reason about cache race conditions. The truth is, all this vendor work is closed, and even if ARM published a rigorous spec in their own language, there's no open tools for processing that language. So there is really only one contender. Because of this, the latest generation of our synthetic toolchain, which we're working on, takes Sail for defining instruction behaviors. At this point, I don't know if we want to migrate there completely and synthesize everything from Sail, because some things are not naturally expressible. It's a functional chain, and In the source, you have functions like the decode and the execute, but in the end, it's just function composition. And after that's done, you end up with a monolith without separate concepts of, instruction format, instruction, assembly syntax, etc. So for now, my binutils stay there with argc. We just invoke Sail with the SMT backend, and it turns out these SMT-lib definitions are similar enough, or pretty similar, to what we fed to the Vex engine.
Let's summarize what we've got. Here is an open source system for automated reasoning about ISAs. It's got a symbolic execution engine, which works by combining SMT and logic programming. It reasons about behavior of machine code, and it infers components of the compiler toolchain from machine-readable ISA spec. It reads argc, and it reads Sail. We use this for construction of JIT compilers. Which ISAs? We did almost all of our validation on POWER and on RISC-V ISAs, and we have had some limited success with ARM and with MIPS. Okay, I hope there is still time for Q&A.
I'm trying to press the button to unmute. Can you hear me?
Yes, now I can hear you.
Right. Yeah, thank you for that. We looked at REMS because for LibreSolve we were looking for form verification, and we couldn't actually find the document that had generated the formal specification. So it says it's auto-generated, but also we found a bug in the divide overflow, I think. I just wanted to ask you if you were aware of these things. Where did you get the actual XML document that generated the formal proofs in the first place?
That's a question for Alistair Raid, not for me.
Okay.
Yeah, because that's them. I mean, we are not the REMS group. I just take the Sail and run Sail with the minus SMT, and that just produces, we've done some experiments with the coq backend, and if I go minus coq, that will give me some coq definitions. So we just process the Sail, so it's okay. Like way down the line, and what happens between the XML, it's really interesting. It's a really interesting question, and I was like, can I get to that XML source myself just to look at it out of curiosity? But I never got around to actually ask.
Because it's an interesting thing, because we had to extract the pseudocode from the PDF specifications ourselves, and found there were actually errors in it or ambiguity. So I was wondering how it sort of begs a question. Of course, if your source material, for your specification is wrong, then the formal proofs are going to be wrong.
Oh, absolutely. This is why I think, and this is where I'm going with this whole presentation, is that maybe we should raise the question of what we should do, like whether we should go the route similar to what the RISC-V people have done, right? So they started from a massive simplification of the ISA spec written in like human English, right? and they got it, you know, from 6,000 pages of the ARM ISA. Their like user level spec is like what it is, 26 or 28 pages of English, something like that. So it's like 8 binary orders of magnitude gain, right? But then they said, okay, no. We have this simulator, the spike, which is written in C, and that's the normative thing. You know, that's if that simulated model behaves like this, then it takes precedence. And the English specification is actually not the normative thing. It's just, and then they started putting in, you know, explanation of history and like background of why certain things are done, and the normative part is the actual simulated model. And then it said, no. Well, now this is outdated because now we have everything written in Sail. So that is the actual definition of the ISA. So maybe in the OpenPOWER space, we should say, okay, well, maybe we should actually have a formal specification, and then everything else is not normative, because in the book itself, right, like in the green cloth book itself, it just doesn't say certain things.
No, it doesn't.
You know, especially when you're talking cache coherence, it's just totally silent. What will happen, you know, when you have out of order, right? Like this is not x86 where everything is just consistent with purely sequential execution, right? You have software visible effects of out of order, and how the out of order pipeline, how it, you know, how it is connected to the store buffers, for example, right?
And dcache b dcbz, which is for clearing a cache row. Things like this.
Yeah. It's just ambiguous. It doesn't like that pseudocode is. I mean, it's very detailed compared to I don't know, the AMD manual, for example, for the x86 is just that there isn't really anything to start with. It's just plain English. But still, it just doesn't clarify. And if you want to have,
I've been asking quite lots of questions of Paul, and Paul has been for clarifying things for us on the OpenPOWER HDL course mailing list. There's just stuff that the normative reference is the IBM Power 9 implementation, from which the spec sort of written behind the thing. So and the fact that there's not been very many implementers outside of that until Microwatt and LibreSoc, these questions have just not been asked. So
yeah, but that's apparently that is all. This is exactly the thing that started the REM's work, right? Because that these are exactly the questions, like, well, what is the allowable behavior here? If I, you know, and that's for compilers too, right? Because you cannot just use the traditional way of testing a compiler, right? Like, oh, okay, well, I just run it on this and it works. Well, yeah. Then you run the same. Run the same code on a different processor, and it still behaves within what the spec allows, and it just is buggy.
Yeah, I remembered there's an example with Pico Risk with their RV formal written by Clifford Wolf. The one person who tested it, he tested it for a customer, and they did something where there was an interaction between two finite state machines. So when a div unit finished, it corrupted one specific instruction afterwards, but only in one particular pipeline. because there would the div unit had left something, some state in their implementation had been left, which corrupted a completely different unit, not related to div at all.
Oh yes,
And
yes,
those
yes,
things are
yes,
very key to
yes,
define.
yes. I remember that one. Yeah, Clifford
Yeah.
likes to. Yeah. And it's like you have absolutely no idea. Like it, you look at it and it appears like, well, what is the connection here? Yeah, yeah. You get really surprising bugs, and good luck debugging them when it only. I mean, we're talking about race conditions, right? And very
Yeah.
rare corner cases. So it's only under load when you have actual, 100 cores under production load, and like once in 10 billion. The executions of a path, it actually breaks, and you try to reproduce this breaking case, and you cannot, right? Because it's just so rare.
No, I totally get the importance of the formal verification stuff.
Yeah.
Oh, thank you.